Hello, everyone. I'm a new faculty at UC Berkeley, and I'm going to tell you about some recent work. By the way, can you hear me well? OK, great. So I'm going to tell you about some very recent work on BlindBox, which enables us to inspect traffic that remains encrypted and protect the privacy of the users. And then I'm going to scope out from this and tell you about a bigger vision that BlindBox is part of, namely computing on encrypted data, which I think can have a lot of impact to industry and to what people use today. So let me tell you what BlindBox does. So BlindBox looks at deep packet inspection. So these devices are widely used today. So Giovanni built some of these, for example. And they're used for various reasons. So for example, they could be used to prevent intrusion and detect intrusion attacks in the network. They could be used to prevent data exfiltration from a company's network. Or they could be used for parental filtering and others. So they're very commonly used. And one thing they have in common is that they examine the payload of the packet, so not just the header. Now, just to give you a very simple, concrete example, consider that Alice and Bob are talking over the network. And in the middle, there's a middle box that is running intrusion detection. Now, this middle box has rules from a rule generator, for example, McAfee. I should have used last line. And based on these rules, the middle box is trying to detect if the traffic is malicious or not. So let's say that Alice, for example, is a malicious user, and she tries to send an attack through the network. And for the moment, assume that the attacks are as simple as the attack word, which obviously is not the case. But in this case, the middle box can just detect, based on the rules, the fact that there's an attack and flag the detection. So the middle box saved the day, but its job is actually not that easy today. And one of the reasons is that a lot of the traffic today is sent over HTTPS. And HTTPS has a lot of wonderful guarantees that it gives us, one of it being privacy, the fact that the traffic is not known to the intermediaries. But in that case, the middle box can no longer inspect the traffic. So the traffic remains encrypted with HTTPS. The middle box cannot do its work anymore because it's encrypted. OK, so as part of HTTPS, users share a secret key, and the data traffic is encrypted with that secret key. So the middle box can no longer inspect the traffic. So what do people do today, right? Middle boxes are still widely used. Traffic is still widely encrypted with HTTPS. So what do people do today? And actually, the solution is a very embarrassing and insecure solution. People basically mount a man-in-the-middle attack on SSL. What they do is they install a fake certificate at the middle box, claiming that the middle box is the server the user wants to talk to. And now, because of this fake certificate, for example, claiming it's Google, the middle box and the user will actually share a key with the middle box instead of sharing the key with the actual server. So now the middle box can decrypt all of the user's traffic and run its detection. Okay? So first of all, this no longer has the guarantees of HTTPS. So first of all, there's no privacy. The middle box can now see the user's traffic. If we have an administrator at the middle box, they can read the user's traffic, so privacy goes away. But actually, a lot of other security issues arise when you break the end-to-end security and guarantees of SSL. So basically, the question we set out to answer in BlindBox is whether we can achieve both privacy and inspect payload. So we want both the privacy of HTTPS and the functionality of the middle boxes. And this is clearly a tension in here. So the answer is yes, and our system BlindBox is the first to show that this could be possible, and is the first system that enables DPI middle boxes to inspect traffic without seeing the traffic. So it's a BlindBox. And the approach is the following. Alice and Bob share a key with each other and send encrypted traffic. The middle box no longer has fake certificates. Now, we want to enable the middle box to inspect the encrypted traffic, so to actually work over the encrypted traffic without decrypting it. Okay? So let me say how we could do that, right? How is that possible? So just to clarify the model really, again, precisely before we go into the design, we have, again, the rule generator that produces rules. We have the middle box and the two users. And a crucial aspect here is that the user should not be able to see the rules because a lot of these IDS companies are not willing to release the rules. And also for classical papers in IDS say that if the endpoints don't see the rules, then it's easier to catch them and it's harder for them to evade detection. And in terms of the threat model, what we want to prevent against is an attacker who actually sees all the traffic at the middle box. So this could be an administrator that sees the traffic. OK, so within this powerful threat model of an administrator that can see everything at the middle box, we have three goals we want to provide. So one, we'd like to have strong privacy guarantees. So we'd like to use a security notion that already exists and it's well studied. We'd like to be practical, and this is really hard because network rates are on the order of microseconds. So not a lot of cryptography remains that could be used in this setting. And we also want to have a wide range of functionality because some of these rules can be quite sophisticated. For example, they could even be regular expressions. So it's clearly very challenging, and we're very ambitious here. But actually, BlindBox achieves these goals. So let me tell you how. So what we built in BlindBox is an enhanced version of HTTPS called BlindBox HTTPS. And with BlindBox HTTPS, when a user sends a message, the message gets encrypted through SSL as before. So we don't change SSL. But then on top of that, the traffic goes through BlindBox Encrypt, which tokenizes the traffic into keywords and encrypts each keyword. Now, these encrypted tokens are sent to the middle box, which is able to run the detection on encrypted tokens and then make decisions if it discovers an attack. And then the endpoint receives the traffic and performs some verification. So let me give you a sense of how we do this detection on the encrypted traffic and how we encrypt the traffic to enable the detection. So the very first step is something that we have in the security community, which is searchable encryption. So this is a really cool primitive that allows you to search on encrypted text. So you can search an encrypted keyword over encrypted text, and all that you learn is that there's a match at some point or not. But unfortunately, none of these were really satisfactory for BlindBox because these schemes are split into two parts. Some schemes are deterministic, which have the property of having weaker security due to frequency analysis, but they are very fast because you can build indexes at the middle box and locate and find attacks very fast. And randomized schemes are actually, they have high security, they don't permit frequency analysis, but they're very slow because you can no longer build indexes. And in the case of BlindBox, we really wanted both because we wanted the security of the randomized schemes and we wanted the speed of deterministic encryption. So as part of BlindBox, our first contribution was to construct such a scheme that is as secure as randomized schemes and as fast as deterministic schemes, and then to construct a detection algorithm based on this. So I'm going to walk you just very fast through the technical details, just very high level. So our new encryption scheme relies on the fact that the middle box has an AES encryption of the rule under the SSL key. And I'm going to mention at the high level how it obtains this encryption. But then the user takes a message, as I mentioned, tokenizes it as part of BlindBox HTTPS, and then encrypts it. And this is our encryption scheme. And I'm not going to walk you through it, but basically, at the high level, it has the following nice properties. You can check for equality between a rule and a token by just taking the encryption of the rule, using it as a key to encrypt the salt, and matching the second term. The second is that it's a randomized encryption scheme due to the salts, which are random. And third is that actually it's fast. It can run at network rates because it only uses AES, and we have AES instructions in hardware. OK, and moreover, on top of this, we are actually able to build trees because we have a very careful schedule for how we choose the salts in a way that preserves the security, but enables us to pre-compute some indexes and adapt the indexes over time, so we can have a very fast lookup. Okay, so one last bit of the design that I didn't mention is how do we get these encrypted rules? And that's not that straightforward because the middle box doesn't have the key to encrypt, and it shouldn't have the key. And also the user shouldn't get the rules. So for this, we use really cool primitive from the crypto community, namely secure two-party computation, which enables the middle box and the user during the SSL handshake to produce this encryption scheme, this encrypted value together without sharing with each other the rule or the key. And we have a specialized protocol to make this very fast. Okay, so I gave you a sense of how the equality part works in BlindBox. And just to give you a very quick sense of the security, the point is that the middle box learns only if a malicious string matches at some location, but it doesn't learn anything else about the other locations. And in the paper, we actually explain how we support regular expressions, and I think it's a really cool protocol because we don't know how to do it entirely over encrypted data, but there's an interesting privacy model that you can provide in this case and actually enable them efficiently. Okay, so we implemented BlindBox, and I just want to mention that it covers a lot of applications already, so only the equality part that I told you about can support already watermarks, checking if exfiltrated documents contain watermarks, and parental filtering, and a bunch of the IDS rules. We even ran it on some of the rules from last line. And the second protocol with the regular expressions actually supports all these rule sets. So in terms of performance, actually, the middle box is very fast. It's really competitive to Snort. So the detection of the middle box is competitive to Snort. In terms of the transmission time, we increase it. So page load time would become 15% to 100% slower. And the one part that's still slow is the SSL handshake. And this is slow if you do handshakes very often, if you have short-lived connections. But if you consider long-lived connections between enterprises and clouds, then that's not a problem. Okay, so far I gave you a sense of BlindBox, which the idea is that we want to do deep packet inspection over encrypted traffic. So we really want to keep the privacy of the users while enabling the functionality of the middle boxes. And BlindBox is part of a bigger vision, the one of computing on encrypted data, which was initially started by cryptographers. And our work showed that you can actually do it in practice for systems that are used today. So to give you a sense of other systems that we could build with this approach, here are a few. So CryptDB is actually a database system that is encrypted, and you can process SQL queries over encrypted data, a rich set of SQL queries. So for industry standard benchmarks such as TPCC, CryptDB had an overhead of 27% compared to MySQL. So this can be quite practical. And CryptDB already has had some impact. So for example, SAP has a system that's based on CryptDB, MIT Lincoln Laboratories, Google's encrypted BigQuery is based on CryptDB, and a few others. There are a bunch of startups right now that are doing this. And also a few other big companies that seem to be using this, although they didn't quite say openly that they're using CryptDB. So for example, SkyHigh is using all the encryption schemes in CryptDB. And Microsoft recently released a service called Always Encrypted. So the cool thing with computing on encrypted data is that your data is always encrypted at the server. It's not just encrypted at rest, on disk, or in transit. It's encrypted all throughout the computation. Another system we were able to build with this is Myler. So Myler allows web servers to run and process encrypted data. Of course, the confidential data. And with Myler, we were able to build a web platform that when you write your application in the web platform, ensures that the web server only gets encrypted data, encrypted confidential data. And actually, a hospital in Boston is currently using Myler in one of their medical applications. And then we were able to do location applications. So for mobile applications, you have a lot of map or location-based systems in which you want to hide the path of a user, but you still want to be able to aggregate information, such as how crowded is a certain street, what's the traffic jam looking like. And we're also able to show how you can do machine learning classification over encrypted data, and BlindBox now shows that you can actually do traffic inspection over encrypted traffic. And we have a few other systems coming up. But the bottom line that I want to mention is that computing on encrypted data can be practical for a set of systems that we use today. And it really gives you, at the same time, confidentiality and functionality. So you don't have to choose only one anymore. And I think that this can have a lot of impact to industry. So I already mentioned some initial impact, but I think this can permeate even more into what people use today. Okay, thank you.